Hello, everybody. Hi, thank you so much for joining us. My name is Jennifer McConnell, and I'm the product manager here at Protochips. And today we're kicking off our new webinar series surrounding sample preparation for in situ transmission electron microscopy. We felt that this topic was an important one to focus on because sample preparation is such a critical component to a workflow that can really affect reproducibility of an experiment as well as the validity of the results. I guess this can be said for really about any analysis technique. However, when you're working at the nanoscale, this means that even small variables in your sample preparation can cause really great differences. Our company has chosen to focus on, the entire workflow for in situ TEM, not just providing TEM related hardware, but everything from sample preparation to data collection to how we're scaling from the bulk scale to the nanoscale, so the environmental capabilities of our systems, and all the way to data management and analysis, because all of these can make or break your success, and they need consideration. The success doesn't solely lie in the specifications of the in situ hardware itself. So again, this series, we're focusing on sample preparation. You're going to learn some really valuable tips and tricks and considerations from several different experts who've been doing this for years in all areas of in situ TEM sample prep. So before I introduce the star of today's webinar, I've got a couple of housekeeping items I'd like to cover. Everybody's going to be muted during the talk due to the audience size and to prevent unintentional interruptions while our speaker is presenting. If you have questions for her, please enter it in the questions box on your GoToWebinar panel, and we're going to have a Q&A session at the end, and we'll address your questions at the end. There's going to be a short survey that pops up after the webinar. We would greatly appreciate it if you take 3 seconds to fill that out to help us out in the future. And a certificate of completion will come to your email after the webinar if that's something that you are looking for. Okay, so without further ado, let me tell you a bit about our speaker, and then I'm going to hand the mic over to her to take over. So today we have Dr. Nynke Krans. She did her undergraduate studies focused on chemistry and nanomaterial studies at Utrecht University in the Netherlands. And during her undergrad, she also spent time at Johnson Matthey, Sonninghamn in the UK, for an internship in exhaust catalysts. Therefore, she started her PhD under the supervision of Professor Krijn de Jong and Dr. Jovanna Sessevic in the group of inorganic chemistry and catalysis at Utrecht University. Her PhD work was titled Iron Oxide Nanoparticles on Support Materials and was focused on the investigation of nanoparticle attachment to various support materials for the Fischer-Tropsch catalysis reaction. In situ liquid phase electron microscopy was used in this work to directly observe the attachment of nanoparticles in real time and at the nanometer scale. After her PhD defense in 2020, she started her job as a nanosafety government advisor at the Netherlands National Institute for Public Health and the Environment. And in 2021, she then started her job as an application scientist at Protochips, which we have been very lucky ever since to have her here. And so I'm very excited to hand this over to her. Nynke, thank you so much for preparing this talk. I'm going to turn my camera and mic off and let you take over. I'll be back for questions.
Thank you so much. And thank you guys all for coming and registering for our webinar series. And I'm obviously very honored to kick this off. And today I'll be telling you something about considerations and applications within closed cell in situ electron microscopy, although I will be touching a little bit on other systems that use vacuum in situ microscopy as well. I'll start off pretty basic, but I'll dive deeper into the considerations and experimental preparation in very quickly as well. So let's start off with what is in situ TEM. So for those of you guys who haven't worked with in situ TEM before and have worked maybe with traditional electron microscopes, you might already know that a traditional electron microscope requires your sample to be in vacuum. And to do that, most people actually dry their sample on a TEM grid, which is usually made out of copper and carbon, could also be gold or titania. But the problem with this is that any sample that is usually studied in operando mode don't typically operate in a vacuum. They operate under a liquid with maybe electrochemistry or heating, or maybe with gas and heating or other heating electrical currents. And people have thought about maybe taking a material out of this reaction by either taking it out and quenching and then embedding, or if it is in a liquid, freezing the sample. So then you can take a snapshot of that reaction and look at what the reaction is doing to your nanoparticles or nanosample during your reaction. However, this is not the same as really looking into what is happening during operando mode using in situ liquid imaging, like you can see with these fish. So why would you want to do in situ microscopy in the first place? So normally if you do analysis such as XRD or Raman or anything else, you're looking at an aggregation of reactions. So basically what you're doing is you're looking over an overall reaction on how your material is either stable or reacting or the activity of a material. And that means that you're looking at the bulk of your reaction. And as these two pictures you can see here, a nice bulk image can be represented and you can learn a lot about your reaction already. But this is not the same as looking at the nanoscale, where you can see all the different type of reactions happening that are happening 1,000 times at once. And if you want to change something about your bulk image, it is really important to understand what your nanoscale is doing at the same time. Are my particles changing size or shape? Is there a phase transformation going on? And this is the information that in situ microscopy can give you. So to design more efficient materials for the future for any application, it is really important to learn something from the nanoscale. So I'm going to introduce to you a couple of different ways of doing in situ microscopy, starting off with the Fusion AX system, which is capable of doing either heating or electrical characterization together with EDS in your microscope, which is elemental characterization, or both of them. And in this case, your sample is situated on an E-chip instead of a normal TEM grid. And this E-chip is made out of silicon and silicon nitride. The E-chip delivers stimuli to your sample from the holder. So you can see over here, there are 6 pins on the holder that deliver the stimuli to your sample by either adding current or resistance and then heating or adding electrical characterization. And how do we prepare the samples on the E-chip is something that I'm going to go into detail afterwards. This system specifically is capable of heating either up to 1200 degrees Celsius if you're just doing heating, or doing electrical measurements at a maximum current of 100 milliamps. And if you want to do them both, you can go to 900 degrees Celsius with a maximum current of 100 milliamps. A second way of doing in situ microscopy is by adding liquid to your environment. But obviously we don't want to just add liquid into a microscope. So therefore we have designed a system that can encompass the liquid into a cell type of environment. So basically you're creating a miniature cell that has liquid inside and can also add other stimuli such as mixing your liquids, heating, or doing electrochemistry. So you can observe any reactions, nanoparticle growth, live cells, lipids, doing electrochemistry, or starting looking at self-assembly of materials, all in this cell. And what does it look like when you put this cell together? Well, you can see there's an O-ring that seals everything inside, and then there's 2 of these E-chips, one delivering the stimuli and the other one making sure that you have a complete cell. And you will observe your sample through this tiny slit in the middle, which is 50 by 550 micrometers. And everything comes together with a lid and 3 screws so the liquid doesn't come spilling out. Well, that's a beautiful rendering, but it's also nice to see what this looks like in real life. So this is one of my colleagues actually assembling the cell. You can see how tiny everything is. The bottom chip, so the small chip, is only 2 by 2 millimeters. So you can see how much precision you need to put this together. And this is why we've made sure that the holder has already got almost everything together, so you don't have to do any alignment. You basically just put the chips in and they're already in place. And you can see here also that she's adding a droplet of water to make sure that there's always liquid in the cell before she can start mixing and flowing things from the outside. And the last thing one final thing she does is to add the top chip in so that everything is nicely sealed together. And the last step is to add the lid and the screws, which I usually think is the most difficult part because they're so tiny, those screws. The final system that I'm going to introduce here is the Atmosphere AX system, which is our gas cell system. So this looks very similar to our liquid cell system. That's why I'm not showing the holder here, but just the whole system, because it comes with a lot of things. It comes with a manifold, which can encompass a lot of gases, and you can mix these gases and you can heat the sample up, but you can also work with vapor. And due to our large chemical compatibility, you can add a lot of different types of gases and vapor and heat to a maximum of 1000 degrees Celsius. And additional to that, we also have an RGA that you can couple to this system, so you can analyze your gases, either your products or your reactants, and see what's happening during the reaction. And last but not least, I'm just going to very shortly put a point on this as well, is that we have this all working together with our machine vision software, which is called Axon. And Axon basically takes all the information from your microscope and your holders and puts it all together so that you have one software that you can use for your data processing, but also for your data analysis and everything together. And this basically makes sure that you can do all your analysis really quickly and simply. You don't have to work with different softwares together. So my talk today will encompass two things: experimental preparation and consideration when starting in situ. And I'll start with the experimental preparation and how to start and really think of doing your experiments. So the first thing you actually are starting when you are thinking about doing in situ is to start thinking and not immediately start doing. We hear a lot of people that immediately want to jump to the microscope. They get this new equipment, they're really excited. They're like, okay, I'm just going to immediately do electrochemistry in a microscope, or I'm immediately going to do my catalysis reaction. But we encourage people to first start and really design their experiment before they immediately jump to the microscope. And there's a couple of things that you need to think about when you're doing your experimental designing. First things first, is especially when you're working with a closed cell environment, is there is a maximum sample size that you can use. And this maximum sample size is 5 micron, because our two chips that are spaced together have a spacer that is maximum 5 microns in width. So that means that you're actually wanting to be a little bit lower than 5 micron, because if you're exactly on 5 micron and there are some particles that are bigger, you have a chance of breaking one of your windows. Not only that, but obviously we're doing transmission electron microscopy or scanning transmission electron microscopy, but we want to have something that is actually going to transmit those electrons. So having really big, thick samples might actually give you very bad contrast and resolution, and you're not going to be able to see anything happening on the nanoscale. So choosing smaller size samples with maybe a higher Z contrast, if you're doing STEM, will give you higher resolution, therefore better results. Doesn't mean that carbon samples are not an option. Obviously, those are an option too. It's just something to think about when you're starting off with these kind of experiments. One thing which is really important to think about is also to check what is already possible and how your sample might fit into this and how your experiment might fit into this. Our holder and our chips are made of certain materials such as titania. We have PEEK material in there. We have silicon as a chip. So some chemicals might not do that well with these specific experimental parameters that we already have present. For instance, if you want to have a very high base, sodium hydroxide, with a silicon E-chip, might not go that well, especially if you're heating up. You might just melt the chip and therefore cause damage eventually to your microscope. So checking the chemical compatibility is really important. But next to this, you're doing in situ in an electron microscope. It might be good to think about that you want to have things that you actually can observe. We, for instance, have had people ask us before that didn't have that much experience yet, can we observe hydrogen gas interacting with our nanoparticles? Yes, this is possible. If your nanoparticles are undergoing some type of reaction, for instance, they're changing in phase, they're changing in shape or size, or they're walking around doing sintering. But if you want to observe hydrogen molecules interacting with a nanoparticle surface, hydrogen molecules are not something you're going to be able to see in any transmission electron microscope yet. So really think about something that can change in some ways or modify in some ways during your reaction. The last one that I'm going to touch upon here, but we'll talk about a bit more during considerations, is the resistance of the beam. Obviously, we're not doing the same as doing something ex situ where there is no high intensity electron beam present. We always have that beam to take into consideration. So when you're doing any electron microscopy, even just being in vacuum, you will have that beam to account for. And one good example over here, you can see over here, that is something that we took with our Axon dose module. So you can see that we've taken a ZSM5 zeolite from the company Zeolis. And in the beginning, when we start measuring in TEM mode, we can see beautiful FFT spots here. And we can see that the sample is nicely crystalline, which is something that we expect. But after a while, using a dose rate of 519 electrons per angstrom square per second, these spots start disappearing. We can see that even better when we are looking in the software. We can see that these spots are disappearing over time. We don't see much difference on the zeolite itself. They might be shrinking a little bit, but we don't visually see anything different. If we now, after only 1.5 minutes, would want to try and do a reaction that needs this crystallinity of the zeolite, we wouldn't see much happening, just because we've been on this zeolite with our beam a lot, and because we've lost our entire crystallinity in the meantime. So dose is extremely important, also already in vacuum. So then we have thought about our experiment. We thought about a great experiment to do, but now we come to more choices. And these choices are in your e-chip choice. We as a company are called Protochips, and this means that we've actually started with designing a lot of chips, and we have loads of experience in that as well. And that means that we have very many choices when it comes to e-chips. I know for liquid only, we have over 300 different combinations that you can choose from. And this can be a little bit overwhelming when you're starting off. So I'm just going to explain a little bit about the e-chips and why you would choose something over something else. And we're starting off with these open cell configurations where we have a choice of different coatings, for instance. We have non-coated chips, we have silicon nitride coated chips, and we have wholly carbon coating. Non-coated chips obviously would not do for any cell configuration because these have holes and then liquid or gas will seep out into your microscope. So for any cell configuration, we always have a silicon nitride coating on our transparent window side. For our open cell configuration, so heating or electrical or both thermoelectrical measurements, you can choose non-coated, and these would be very nice for instance, doing nanowire or carbon nanofibers or anything that has a longer configuration. FIP would be a very nice example for this, to use this for FIP lamella. And silicon coatings or wholly carbon coatings, depends on your nanoparticle size. It will be nice to deposit something on top. For the liquid, it is good to know that our top chips have the stimuli. So there's a top chip that has no stimuli at all, just a silicon nitride coating, which is very nice for nanoparticle self-assembly, nanoparticle growth, but also for life science examples. So if you want to look at viruses interacting with different kind of liquids or those kind of applications. We have an electrochemistry e-chip that includes a working counter and reference electrode, and we have these in different configurations as well. And we have a heating e-chip with a tungsten coil that can heat up the liquid up to 100 degrees Celsius. And for gas, we have a couple of configurations that you can choose from, always including heating and always including that silicon nitride coating as well. And you can choose if you want your sample on the top or the bottom. And in the next slide, I will explain a little bit about why you want to make that choice. Lastly, we also have a couple of things like blank chips. So these are really nice for people that are practicing for the first time putting the holder together and don't want to use any of the expensive chips. Or if you want to see if your holder is leak tight without using any of the chips to see if there's any leaks in your holder due to maybe dust or other things that have come onto your O-ring. And the last are the masking chips that I will also tell you a little bit more about later. I was talking about this top and bottom configuration, and this is actually quite an important choice as well. So this is your next choice. You have now chosen your chips, but now you need to put your sample somewhere. In liquid, obviously, you can have your sample floating around as well. You can have your sample just in the liquid itself. However, there's a small problem with that, and that is that there is still Brownian motion and your particles start walking around everywhere. So it might be tricky to find your sample. And this is why most people opt for putting a sample and drop casting it still on either the chip itself, bottom or top. Having your sample on the bottom window makes it optimized for TEM, so transmission electron microscopy. And you can see that in this image over here, you can get beautiful resolution, even if there's gas present from these palladium nanoparticles on a titania support. For the sample on the top chip, you can have an optimized sample for STEM or HADF, STEM, dark field or bright field, and also for EDS, because your EDS detectors are usually situated on top, and therefore your signal can get easily to your EDS detectors. And this is especially important for liquid cell applications. For gas cell, obviously, as well, but gas doesn't deflect your electrons as much as liquid. And you can see here an example of a paper in 2015 in ultramicroscopy, which I highly recommend reading, is how the electrons scatter from your electron beam compared to putting your sample on the top or on the bottom. There's another paper that I haven't cited from Niels de Jonge. That's also a very recommended read because he's explained in much detail why you want to use bright field over dark field STEM or bright field over dark field TEM with different configurations. But the main rule that I want to give you here is that bright field STEM, also dark field STEM, is best for using very thick liquid layers when analyzing thick samples in general. And what they've done here is they've taken some gold nanoparticles, and they haven't even put liquid, they've just put a block of resin on here to observe what configuration is best to get the best resolution. And for STEM, you can imagine that you have this very fine tip that you're scanning over the surface. And if you would put your sample on the bottom and that fine tip needs to go through that liquid layer, it will always get very dispersed very quickly. So that's why putting your sample on the bottom will actually result in very blurry images compared to putting the sample on top. For TEM, this is almost the opposite because now we're working with a broad beam and your detector is at the bottom. So if you have some beam scattering in the beginning, it doesn't matter too much, and therefore your sample at the bottom will have a much better resolution than on top. But you can see the difference between TEM and STEM here as well for thick layers of liquid. Before putting your sample on top though, it's always good to have a very clean chip. So make sure to clean your chips properly. And one of the steps here could be plasma cleaning or glow discharging if you don't have a plasma cleaner. And plasma cleaning does a couple of things. First of all, it removes a lot of contaminants from the surface. So if your chip has been sitting in a box for a while, you can use it to really clean the surface of your chip, but also it makes it very hydrophilic. And this is nice for liquid, but also for gas applications because you want your sample to be nicely dispersed on your windows and not have really big clumps there. So plasma cleaning your chips makes them clean, but it also makes sure that your sample is nicely distributed over the chip itself. And in this research from Professor Dr. Sascha Storm from the Joseph Stephan Institute, they showed how long your chip keeps being hydrophilic after being plasma cleaned. And immediately taking it out of the plasma cleaner will make it a little bit more hydrophobic, so it's not perfectly hydrophilic. But after that, for over 15 hours, you can just have your chips sitting around without changing too much in hydrophilicity. After that 15 hours, it gradually goes up in hydrophobicity. So this means that if you want to use your chip afterwards, it would be great to plasma clean it one more time. The chips can handle that, so that's no problem. It's more that you then just lose your hydrophilicity. So now we've made a choice for our experiment. We made a choice for our e-chips, and now we want to put our sample on our e-chips after plasma cleaning. And there's a couple of ways of doing this. There's drop casting, there's dry loading, and there's also sputter coating. And there's plenty more ways to do this, but those are the three main things that people usually use. And for drop casting, this is ideal for if you're using some kind of nanoparticle or a nanoparticle on a support. Because in this case, we are assuming that our nanoparticles can be dispersed in a liquid, most likely ethanol or toluene, something that evaporates quickly. And then we would always advise to first sonicate your sample so that the big chunks of sample are broken up into smaller bits and you have a nicely dispersed sample. You then take your micropipette, and this micropipette can be used to really take very small amounts of liquid. And the idea is to put a tiny droplet of that liquid with your nanoparticles inside on the chip and dry it. It is always a good recommendation to do this under a stereoscope so you can really see where you're putting that sample. And nowadays there's also capillary micropipette tips that are really great to be even more precise than what is shown on these images. And it's also very important to not touch your silicon nitride membrane while doing this because it will probably break, and then you will have a hole in your chip, and that will make a leakage occur. I have an example here from literature. This is actually my own research, so it's always nice to show this. In this case, what we did is we added in advance, we added some carbon nanofibers to our e-chip, and we drop casted and dried these on our e-chip. And then we flowed through iron oxide nanoparticles through the cell to look at the assembly of the iron oxide nanoparticles on the fiber. And what you can see here is that because we drop casted that fiber first in place, we can really see the fiber from our bright field STM images. And because we're flowing through our particles from time 0, we can really see how the self-assembly occurs and what is the optimum amount of nanoparticles to put on these fibers, and get a bit more conclusions on how these nanoparticles interact with this nanofiber. So this is a very nice way of seeing what it looks like to have something drop casted and in place without moving, and some other things moving around, so you cannot even see the particles coming by because they move so quickly. Dry loading is another option. This is specifically nice for fine powders, something that you can grind in advance to make sure that your powders are super fine, and something that might not be able, or in some way might not be stable in a liquid. So in this case, you would take your e-chip, most likely in your box where it's nice and stable, and you would put a little bit of powder on the center of the e-chip. You can even, if you would like, put this on a vibrating plate, so it will nicely disperse. And after a while, you can tap off the excess of powder. Always investigate under a stereoscope again if there's enough powder on your e-chip, and you can use this to really nicely add some fine powders. You can also combine this with the shadow masking method, which I'm going to show you over here, which is very nice for sputter coating, because in this case, we take one of our functional e-chips and add a masking e-chip on top. And this masking e-chip has a hole that has the size of your windows. This will be on top in your shadow mask, so it's all nicely aligned together. And then you can either sputter coat or drop cast or put your dry loading sample, so the sample only comes into the area of your window where you might want to do your reaction on. This is nice for samples that you don't want touching anything else. So for instance, you don't want them touching your electrodes, or you don't want to touch the counter electrodes if you're doing liquid cell. Last but not least is FIP preparation, and I won't spend too much on this because we have a very nice webinar in December on FIP preparation and another one in January coming up as well. So I will only say that there are chips available for a specific FIP preparation, but Dr. Veschner-Strotz and also Roberto Garcia will tell you much more about this in December. So if you're interested, please register for the rest of the webinars. So one thing that I also do want to touch upon is doing electrochemistry in liquid cell. One thing that we've heard a lot from the field is obviously there can be a lot of gas generation during your electrochemistry experiment, and this is something to keep in mind during your preparation, especially if you're adding electrolytes with saturated gas, for instance, saturated CO2. If you're not doing saturated gas electrochemistry, so no saturated CO2 or oxygen, then one thing that we always recommend is to sonicate your electrolyte beforehand to remove as much oxygen from your sample as possible, because most gas generation is oxygen or hydrogen during your reaction and will look something like this. This can dry out your entire cell and make sure that you don't, or you're not able to do any of your reaction anymore. And next to that sonication, we also have now these new e-chips that can actually make a really nice way of still observing your working electrode, which is here on the window, while your counter electrode might be making a lot of bubbles during your experiment. Other things to take into consideration here is that you can use very small CV steps, so you're not immediately going to that maximum voltage if you're doing cyclic photometry, using flow to remove those bubbles, and doing that plasma cleaning so that your chip is hydrophilic and your bubbles will flow off easily. An example from literature on doing some more oxygen evolution reaction in situ microscopy, also in liquids, is here from these manganese oxide nanoparticles. And their idea was not to do this with electrochemical stimuli, but using a controlled environment where they chemically induced this oxygen evolution reaction. You can see the magnesium nanoparticle, the manganese nanoparticles over here. and they use the chemical way of doing oxygen evolution reaction. And one thing that you can see over here is that when they start adding their electrolyte inside, it starts forming oxygen on the outside, and they can exactly see on the nanoparticles where the oxygen is formed and how this changes the nanoparticles over time. So this brings us to the next part about considerations when starting in situ. And as I told you before, one thing that is extremely important is the dose and just general microscope effects. There are so many challenges in situ electron microscopy, and we usually say it's always a trade-off. So everything will be happening at the same time. You can have electron beam interactions that will affect your resolution, sample movement, and sample stability. If you're working with liquid, there's always liquid thickness to take into account, or sample thickness in other types of experiments. And then there's other imaging parameters such as your resolution, your magnification, your apertures, anything that can also affect your resolution, your sample movement, and electron beam interactions and stability. So dose is a very important part of this, because when you put a high intensity electron beam on your sample, you can have a lot of site reactions such as charging and heating, radiolysis, which I will talk about a little bit, hydrocarbon contamination, sputtering, and atomic displacement as well. There are very good papers you can read about this if you have no knowledge about this yet, so you can understand what your electron microscope is doing with your sample in the first place. So knock-on damage is one of these things that always will happen when you put an electron beam on your sample. But already in research, there has been quite a lot of literature written about what are certain thresholds for certain samples. For instance, the knock-on damage threshold for graphene is 80 kilovolts, kiloelectron volts. So if you stay below that, you will at least not have knock-on damage. Does not mean that you don't have problems with the other things, but at least knock-on damage is taken out of the equation. Charging is an important one. We can see both in gas and in liquid cell that if your window charges up, your sample might either disappear, so jump off the window because both of them are charged, or in other kinds of reactions, you can even see particles starting to align towards your window because you're charging your window and your particles are also charged, which is something you can see here. All these particles are attracted to the window because the particles and the window are both charged. Heating, local heating can be an issue, specifically in gas cell, but also in liquid cell when using organics. This can cause damage to your sample as well, also in vacuum. And the last one is hydrocarbon contamination, which can even obstruct your viewing area. There are other types of damage that can also happen. In our next webinar in November, Savannah Turner will talk a lot about this as well, so I won't go into much detail there. But radiation damage in the TEM and SEM, this paper is a very good one, a very good read for this. Now, there's other things that can also affect your sample. So when we're doing in situ microscopy, but also microscopy in general, thermal expansion is one of the things that I really want to talk about, because once we're heating our sample at the nanoscale, everything will start expanding. This is just what happens to your sample, but also to the chips. Everything starts expanding. And because we're at the nanoscale, this will have a huge impact on the stability of your sample. While we are heating, the sample might go completely out of the image. And this also accounts for when you're, for instance, adding gases and you're changing the pressure really rapidly, your sample might also go out of the field of view. Just to have an example of this and look at just what is happening already, we can take a look at drift and bulging. So changing from the bulk scale to the nanoscale might already alter your melting temperature of your nanomaterials. So a nanoparticle might melt hundreds of degrees differently than your bulk material. And if we're looking at drift rates, you can see that if you have a temperature ramp of different degrees Celsius per minute, that will also alter your drift over time, with higher temperature ramps having higher drift rates. So this is something that will always happen and something to take into account of, and has been battled mostly by doing drift control by, for instance, using machine vision technology. Other things such as magnetic field charging and sample reaction might also make your sample move. And one really funny one that I really wanted to show you as well was this reaction that my colleague did in NC State. So she was looking at these nice gold nanoparticles, beautiful atomic resolution at just in vacuum. And she wanted to know what would happen if you started talking loudly in the room, or singing in this case, because the microscope also sometimes deserves a serenade. So she started to sing, and you can see immediately that these kind of vibrations have a huge impact on your atomic resolution imaging. So external vibrations, walking in heels is never a good idea around the microscope, or please don't sing to your microscope either. So your resolution decreases when you add anything to your microscope that increases the thickness or scatters your electrons. And I talked about that for liquid, and in gas it also happens, but in less of a extent. And that's what we saw as well. We can still have beautiful atomic resolutions while working in gas, but adding gas will reduce your resolution as well. And this is even worse in liquid, but in liquid we also have radiolysis. And this is a very important thing to take into account. So if you add your high intensity electron beam to, let's start off with water, water might start splitting into all these different radicals, and all these different reactions are happening at the same time. So these are effects that are seen in liquid cell electron microscopy, but also when adding a vapor to your gas cell electron microscopy reactions, because a vapor of water will also have a lot of radicals formed by the beam, and these might start interacting with your sample and therefore start breaking down your sample or adding reactions, even showing reactions that shouldn't be there. Each liquid has their own radiolysis chemistry, so it's really important to look up, I'm using this liquid or I'm using this vapor, what will happen to my chemicals. So with water, it is quite well researched for now. Also in different papers, we will see what water does when an electron beam hits it. But also organics, there's lots of things online that you can find in different papers on how organics react to an ionization energy. Ethanol, for instance, will obviously form different radicals than toluene or water. And if you want to know which radicals are causing damage, you can easily exchange a liquid and see, for instance, if you're exchanging water for toluene, most radicals that will be formed will be these hydrogen radicals. So if you want to know, oh, are my hydroxyl radicals causing a reaction, you can switch to a different liquid and see if the same breaking down reaction is still happening. So what happens exactly when you add your ionization beam to your water? So these are all these water molecules. You can see over here, they have their own electrons. And if a beam hits an electron, it can push out different electrons from your water molecules. This will cause solvated electrons to form. These are highly active species. They're completely immediately wants to react with something else, reduce different parts of your sample, or start forming different components. And your water molecules can split into acids and OH radicals. Another thing that can happen is that ionization energy can split water molecules in forming hydroxyl radicals and hydrogen radicals as well. These two papers are really nice to read. I know that at the moment there's more research being done on how these radicals form and how this changes pH and how this changes your liquid environment. But I would definitely recommend reading the paper from Sophie Lequer and from Nicholas Schneider, because they really show on what liquid does when hit with a high intensity beam. And especially these two papers show over time how much of the radicals are being formed and with which dose rate and how fast they form. Luckily, not everything is as doom and gloom as I explained. There's also many papers that show how you can combat radiolysis, not only by changing your dose to a very low dose, making sure that you have an accurate dose reading and understanding what your dose does, but also, for instance, by adding buffers or ligands to protect some of your nanoparticles in here. In this case, we're looking at gold nanoparticles, and they were looking into, okay, how can we protect our gold nanoparticles from anything that is happening in our liquid? We can add different pHs, we can add salts, or we can even add ligands. And what they saw eventually is that by adding ligands and salt at the same time, by screening their particles and making sure that there was a counter reaction happening at the same time, they could stabilize their gold nanoparticles in liquid completely. Adding too much salt, though, would actually completely dissolve their gold nanoparticles and being exactly in the middle would actually make the particles slightly dissolve and then coalesce and grow. However, people have also used the beam for their research. So in this case, in this paper from 2021 in Advanced Materials, they were looking into how can we grow gold nanoparticles using a gold chloride solution at different temperatures, and how do the temperatures change the kinetics of the reaction. And you can see immediately when they start off with the temperature and then start adding this beam in dark field STM mode, you can see that the particles that are growing have completely different sizes and shapes depending on the temperature. The dose that we're using was exactly the same. They just wanted to see, okay, if I add temperature, how does it change the kinetics of my reaction and what kind of particles do I form? At 25 degrees, they formed very small, similar shaped round particles, but at 85 degrees, they formed triangles and hexagons that can actually introduce some ideas on how to change nanoparticle sizes and shapes while doing ex situ research and synthesizing these particles. I've talked about charge being in some cases a bad thing, but it can also be a great thing because it can use charge and magnetic forces to start lining up particles. In this case, these cobalt iron oxide nanoparticles that they use a charge of the microscope to actually look at the particles. They came from the liquid and went to the window and even formed these chains because they were magnetic forces acting as well. It's a very interesting paper too if you want to look at self-assembly of different kind of nanoparticles. The last consideration here that I want you to take into account is the bulging of the membrane. In liquid and gas, this is both a problem or something that happens where if you put your sample in this cell with very thin silicon nitride windows in the vacuum, it will bring out the windows and cause bulging. And especially in liquids, this will cause a big difference in resolution from the corners where the resolution is still quite nice to the center where we have thick liquid layers and therefore also a very difficult time seeing our particles. There's a couple of ways to combat bulging as well. Always use a sample or a spacer size that is in the range of what you would like your liquid thickness to be. We have so many different samples, spacer sizes available from 0 nanometers, so dominated by your sample size, all the way up to 5 microns. So you can do a lot of different experiments with different size samples. And you can also adjust your window size, either having a 50 or 20 micron width window, and you can see that that changes the bulging a lot as well. Wider windows will create bigger bulging and smaller windows will create less bulging. Then some people have tried also adding gas to their sample by using the beam to form hydrogen or oxygen gas and therefore thinning out their liquid layers. And another option is to apply negative pressure on the outside of your holder. One thing to always take into account is to work very clean because any debris introduced during assembly will make your liquid layers thicker. This brings me to the last part of the presentation where I'm going to talk a little bit about bulk versus nano. So when working in bulk and going to the nanoscale, there might be some other things that you take into account. Heating a sample will not be done in a reactor, but it will be done on your chip. And therefore, it's really important that your chip has uniform heating all over. This is why we use silicon carbide as a heater instead of coils, because then you can see that the temperature is very equal over the entire sample. In this case, with the shot glass, we can see that everything starts melting at 620 degrees and everything in the center here around the window area starts heating the same. There's a couple of things that can reduce your heating or in effect reduce your heating, which are conduction, convection, and radiation. Conduction basically meaning that your heat goes away through your chip. Convection is that the heat goes away because you're in a vacuum of the TEM, which is much colder than your chip itself. And radiation, the heat is being redirected by the steel of the TEM column. Luckily, because we're working on such a small scale, when we are directly heating the chip, there is usually no convection because we have vacuum. Radiation only becomes really important at very high temperatures, and conduction only presents itself when outside of the silicon carbide of the heating chip. And this is why our chip also acts as a heat sink, meaning that not the entire holder heats up, but just that center part of the chip. Looking at catalysis and doing gas cell, there is also quite a bit of big differences. So obviously there's a limit of range of pressure. We can only go to 1 atmosphere maximum and not anything higher than that, because it is a very dangerous part if you want to go higher in the microscope, because your microscope is vacuum and inside it is 1 atmosphere. So there's a limited pressure range. There's also no particle-particle contact, because mostly your particles are attached to this E-chip. So we don't have the same type of reaction what we had, for instance, for a fluidized bed or any type of catalyst reaction in a reactor. So this is what a normal catalyst reactor in a fluidized bed would look like, for instance. But now we have all our chips or our sample on the E-chip and the flow going over the sample, which will cause different kind of reactions. It doesn't look exactly the same as XC2. However, it's always great to do identical location TEM, where you, for instance, take a chip and put your sample on top and put it in a normal reactor to observe what kind of difference it makes to have a chip in a reactor compared to a chip in a holder. Or if you really want to compare it well, use fixed bed in your XC2 measurements compared to your chip. In catalysis, a lot of people really want to observe usually these type of things, which is precursor addition if you want to do incipient wetness or impregnation or melt infiltration, drying, calcination, reduction, and your reaction, obviously. And what we see most of all in literature is that people have mostly focused on calcination, reduction, and reaction, because precursor addition and drying are just really, really tricky. And one example over here, you can see by a paper from Petra Kaiser, you can see that she's tried to look at how her precursor actually looks like in her silver nanowires. But when putting a just added precursor on her silver nanowires in the electron beam immediately reduced her silver precursor to silver nanoparticles just by the high intensity electron beam. The only way to observe how the precursor was added and how it looked like in the silver nanowires, but was by cooling down the sample beforehand in liquid nitrogen and then quickly observing it in the microscope. So it is a possibility, you just have to have the right experimental conditions. So for precursor addition and drying, the beam does a lot of damage, and it's a lot important to take that into account. Calcination, reduction, and reaction are all possible. And calcination is sometimes more difficult because of oxygen presence outside the microscope. So it might be handy to put everything together in a glove box. For doing electrochemistry, there's a couple of things also to take into account when going from bulk scale to nano. And one thing is that obviously now you're at a nanoscale with nanoelectrodes with a very small amount of liquid. And one thing that has been seen in literature before in 2014 is that if you are reducing your liquid layers to get a better resolution, you're also completely changing your electrochemical CV curve by quenching it completely due to the thin liquid layers, and also usually depleting your electrolyte really, really quickly. So flow is really important here, and most optimally you would like a thicker liquid layer if you want to stay closer to your bulk scale measurements. One thing that is really positive though is that the electron beam doesn't have a big effect on your actual cyclical telemetry curves, which is great. So you will be able to see your reaction even if you have your beam off and on. The only thing that might happen is that if you have a very strong electron beam, that you might start breaking down your sample or your electrolyte in the beam. So it's always good to beforehand check what your vacuum or what your sample reacts like to your electron beam. One thing to become closer to our bulk scale reactions, what we've recently developed is a standard reference electrode that operates outside of the microscope. And these type of experiments were done to observe if we can change our reference electrode that is normally on our chip to something more commercial. Our reference electrode is always located on the chip, and we need to make these out of platinum because that is easiest to fabricate on such a small scale on the chip. A silver chloride electrode, for instance, putting that in that small chip in the electron microscope is really tricky, and it will most likely also contaminate your sample. So in this case, we've made use of the Lugan-Haber principle and using a Lugan-Haber bridge. This means that normally in a conventional setup, you have your reference, counter, and working electrode in one beaker. And now, instead of using a salt bridge, we use a metal bridge where your working electrode and your counter electrode are in one beaker, meaning inside the microscope, and your reference electrode is in another beaker with the same electrolyte. In this case, when we're looking at a ferrocyanide couple, what you can see is even with a conventional or the metal bridge setup, you have exactly the same cyclic voltammetry curves over time with different potentials. And changing this wire in length or thickness or even material doesn't matter too much, and you can all have the same reaction happening as long as your electrolyte is the same inside as outside. And this results in us making this standard reference electrode that you can hook up to any E-chip. So the E-chip doesn't have to change, your holder doesn't have to change, but you can use a standard reference electrode here, and you can use any standard reference electrode. You can use silver superchloride, calomel, or anything else. This means that you can also just purchase this from any external party. And it's really important that your OCP stays very stable when using longer wires. And luckily, we have very nicely shielded wires, so that always happens. And you can see here that what they did for this experiment to check if it works is they first had that same ferricyanide couple on the chip, working with the platinum reference electrode from the chip. And then they unhooked that from the potentiostat and hooked the standard reference electrode on there instead. And indeed, you see a shift, but exactly the same curve. And the shift is just because you're changing your reference electrode. So to summarize my talk, I've talked about some of the different ways of doing in situ microscopy and considerations when doing in situ microscopy. So there's many steps to consider. I don't want to discourage you in doing in situ microscopy because it's also a lot of fun. There's a lot of things that you can do, and there's so many different reactions that you can try. But there's just many steps and parts to consider when doing an in situ microscopy. In experimental preparation, just prepare and think about everything you do well and try and be as reproducible as possible, and understand how your system works ex situ as well before you're doing anything in situ. If you want to know what is possible now, we have whole bibliographies on the website. There's atmosphere bibliographies, Poseidon Fusion, and you can filter on everything that you would like. But for now, this was my webinar. Thank you all for listening and for coming today and for registering. If you want to look at any of the other webinar series, you can use the QR code, scan it with your phone, or go to our website and register. Thank you.
Nynke, thank you so much for such a detailed talk. And I think this was very helpful to a lot of people because we've got a lot of questions that have also come up. And so let's go ahead and go through some of these together. And if it starts kind of running a little bit long, we'll have Nynke reach out to you separately to make sure that your questions get answered as well. So we've got a few related to plasma. Oh, sorry, go ahead.
Yeah, while you're looking through these, I also want to mention that we do have application scientists around the world. So if you have any specific questions about your application, very specific, you can always email us as well, and we'll be happy to reply.
Yes, if you're using our products currently, support@protochips.com is a great place to go because then our entire applications team gets the question and whoever's available at that time can help answer. So there's a few questions related to plasma cleaning, so I'm going to put them together, or I'll start with those since they're related. Which gas for plasma cleaning do you recommend? I'll go ahead and let you answer, and then I'll go with the rest of them. Sorry.
Yeah, so, we usually have argon oxygen, but in principle, it doesn't matter too much. Even with glow discharging, you'll be able to get a nice plasma clean surface. And if you want to try, you can try one of the blank E-chips and just put it in the plasma cleaner because it also depends on the strength. So you can just put it in, drop cast a little bit of liquid, and if it nicely spreads, then you know that you've done a good job. And otherwise, you take your blank chip, put it in again, and see with a different gas or a different strength or a different length of time.
Do you mind recommending maybe a strength and a duration of time? Because that was in the second question I was going to ask.
Yeah, strength, well, this is a very difficult question to immediately answer, but the duration of time is usually 2 minutes. Depends though, because if you're using electrochemical chips with a glassy carbon working electrode, that is really important not to plasma clean them too long because carbon can evaporate in your plasma cleaner. So keep that as short as possible, usually 10 to 15 seconds maximum.
Perfect. And then the last one related to plasma cleaning, I believe, is there any effect of plasma cleaning on the silicon nitride window?
Well, except for that it becomes hydrophilic and you're changing the surface groups, nothing in that sense that can change the thickness or the stability of it. So the thickness and the stability stays exactly the same.
Perfect, perfect. Can the electron beam also heat up the sample and or the electrolyte during a liquid cell experiment? If yes, how can you estimate the electron beam effect on cell temperature?
This is a very good question and something that has been debated a lot in literature, actually. So it's very hard for me to give one. This is a stupid answer because I can't really give a one straight answer. There's papers that have said that the liquid only heats up 1 to 2 degrees locally, which is not very much, and it diffuses really quickly. There's other papers that have seen 10 to multiple tens of degrees difference, but I think it depends very much on if you're using flow. And as long as you're using flow with your electrolyte, you're able to cool down that area as quick as possible as well. So that's one of the reasons why with electrolytes or electrochemistry in situ, we always recommend using flow, not only to replenish your electrolyte, but also to remove any heating effects.
Perfect. And there's more coming in as we're talking some more. So I'll probably pick maybe 3 or 4 more, and then we will certainly reach out to everybody individually to make sure that everybody gets their answers. About the small steps when doing a CV, is it only related to the danger of generating bubbles, or is it also related to the capacity of the holder's electrical instrumentation to withstand harsh variations in potential?
It's a good question, but the holder can withstand quite a bit of different variations. We've even seen people go all the way up to 4 volts with our electrochemical in situ setup. So you can go to very wide variations as well. It's mostly the gas formation, and as well to have a bit more control over what your reaction is doing. So if you take smaller steps of 50 or 100 millivolts at a time and doing 3 or 4 different CVs every time, then you can widen your window slowly and really examine when your reaction is taking place without causing any side effects.
Lovely. Okay. Thank you for the nice talk. For sample preparation by drop casting, would you recommend heating the chip on a hot plate while drop casting or after it to dry the chip?
You can definitely do that. Yes, 100%, especially if you really want to keep it centered and you want to have your liquid evaporated as quick as possible. You can heat our chips up, and Jen, correct me if I'm wrong, I think up to 80 or 100 degrees even Celsius on a hot plate. So they can withstand quite a bit. And if you, what you would then do is you would take your chip, drop cast, and then put it on the hot plate to evaporate your sample.
Let's see. So, hello. I'm working on hydrogen embrittlement of aluminum alloys in humid air. Humid air. I would like to ask if there's a limit to the amount of relative humidity that can be achieved with a gas cell.
Yeah, definitely. This is a very good question because obviously if you go to very high humidity, at some point you will get condensation, and this is not something that we would like to have in our cell, because if you have condensation, it's going to be extremely difficult to get that liquid out of the cell. So our systems are all designed to make sure that you don't go over the condensation limit with different temperatures and different pressures. So this depends on the pressure that you want to use, but we all have this internally designed so that you don't go over that condensation limit and you never start condensating liquid in your system. And this is just in general, you know, if you have a certain humidity outside, at some point it starts condensating. There's a general formula for that I could send through if necessary, so you can see.
Good, good. Okay, let's do one more, and then there's a few that we'll have to follow up with. Is there an alternative to increasing the flow rate that can be used to remove the bubbles during an electrodeposition, for example?
One more time, sorry. Is there an alternative to flow? So in the cell,
increasing the flow rate. So an alternative to increasing the flow rate that can be used to remove bubbles during an electrodeposition, for example.
Well, if we go a little bit back, sorry, I'm just going to quickly go through our slides. One of the things that you saw with these new chips that we have, it's going to be way back, where you saw that the chips actually remove liquid very quickly. That's done with the same flow rate, so you don't have to increase the flow rate to stay with that same e-chip. There we go. And you can see that we didn't change the flow rate here. We just kept the same flow rate, but by choosing the correct e-chip, you can actually remove the bubbles really easily from the working electrode and the counter electrode. This is just an example from the counter electrode creating bubbles, but we also have examples from the working electrode creating bubbles and how this works really well without changing the flow rate.
It also keeps the liquid layer very thin in the viewing area as well. And so you're still keeping a thin liquid layer there, but your bubbles are able to flush out pretty easily. So you're not sacrificing the imaging side.
Exactly.
All right, the questions keep rolling in. So I think we are at our time though, so let's call it. Thank you so much everybody for coming, but I'll share the list of questions with Nynke. You go ahead and enter them in real quick before you leave if you've got a question for her still, and we'll make sure to reach out to everybody and get you some responses to your questions. Nynke, thank you again for the wonderful talk.
Yeah, if you have any other questions and you don't have the time to now type them in while we close down, support@protochips.com. We'll be happy to answer. Yeah.
Yes. Thank you so much. Be sure to sign up for the other webinars. They're in the chat. You can get the link there as well with fib prep and gas cell preparations. And we look forward to seeing you there. Have a good day, everybody.
Thank you.